Okay, here we go. So you've got your sheets.
Yep.
Page 1 only. Page 1 only. So it should be review. So we've been at the beach, right? We've been sleeping a lot. We need to get our minds reoriented to this stuff. So page 1 only. See if you can get through it in 5, at most 10 minutes. Page involves no calculations at all. You're not doing any computing. No numbers, except for the delta H, okay? Everything is very rough sketching, just the idea of it, okay? No computations on page 1.
Bless you. Bless you. We're going to change exactly. Yeah, so it goes. Okay. Oh, I know. I meant the first letter of each one, so.
Well, yeah.
But you gotta make sure, of course, which one you're doing with the changes in manipulation.
Okay, we better got that first thing right. You can check your answer. Better get that right before we go on. So confirm that you are on the right path here. Yeah.
Just basically rough testing it. I know exactly what I'm saying is now we have to do a slope. And that's our approximate.
Just look at your rates. You have a positive or negative rate. Positive, low or high? High positive rate or low positive rate? Low positive rate. What about the next one? Positive or negative? Positive compared to the previous. Higher positive rate. That's all. That's just rough. Just rough. So yeah, you did good.
Yeah, it's going to increase. It's going to get much stronger as you go higher. So like this probably gets yeah, like this. Generally, you do that as fried. So it's really small. And I'm not going to do that. But this is this. Your conversation higher just here. It's going to be close.
Right, so yeah, that's what the instructor tells us to do. It is.
Very rough sketch is exactly achieved. Rough sketch. That's right. So this is find the approximate
So,
Here's the general idea of number one. I saw lots of you had something like this, okay? Any questions? No, do not go on to page 2. Just page 1. Do not flip to page 2. This is not right. All right. Think about what kind of rates of change you have here.
Oh, it's increasing.
It's not really high.
Because yeah, so this starts at origin. You can't really see it. It starts here. Yeah, so that starts there. Just can't really see it very well, but yeah, just go down. It's okay. It's just the idea.
Really high, really great.
Questions on the first one? Yeah, please. Don't use steps for that. Don't use steps for that. We want a piecewise linear function that's trying to mimic the curve, right? One step.
But does that make sense? Because you're going to negative at greater rates. So what's the difference between our accumulation function and rate of change? This is a very important question.
I know.
Changing is
Then I would
right here. It's decreasing.
so if I
That's why the step
Questions on number 1? Anybody have a question on number 1? The approximate accumulation function is not a step function. We need a piecewise linear function, right? Piecewise linear that tries to mimic that curve. So we're going to pick off points on the curve, and we're going to join those points with segments to make a piecewise linear. Then when we pull out the constant rates form the step function, just like before, just like we've done all semester, okay? And again, no calculations, this is just rough, just getting the idea of this whole reverse process. Any questions on number 1? Okay, on number 2, again, you're not going to have, it's not going to be steps, it's going to be okay, now what's different about this one? What about the rates of change? They're negative. I saw lots of you got this. Some of you are drawing up here, but your rate of change is not positive. But many of you recognize, is this a high or low negative rate? It's a higher negative rate, so it's going to be like something down here. Negative or positive? More or less negative than the previous?
Less.
Less negative. Okay? And then getting less negative. But these are all very similar, right? So something like this. Again, just generally here, just a general idea of it, of the exact rate. Okay, anybody have a question? So what's our journey? From exact accumulation to exact rate. And so this is just the idea of it, but we need to now formalize it with some mathematics now. Okay? Any questions before we go on? Okay, so now on page 2, we're going to kind of repeat the process, but look a little more in depth and like I said, put some mathematics onto it. So let's start with you on, what's the first one? Now you're going to use your H, your delta X or H is going to be 0.4. And so you're going to start the same way you did before. You're going to sketch the approximate accumulation function there in number 3A on page 2. Okay? For delta X of 0.4. And we're going to animate this one. Just, are you done with part A?
Yeah.
Should look like this. This is the dynamic version, so, yeah.
If you did like the right with the above progress, do we know what's in life?
It's not, no, so let's just wait a second. Just hold on to your question. Okay, so now as B is review. Okay, so B is review. So without peeking at your notes or looking at anything, can you write so this what this function is? So who remembers? What kind of function is this
Piecewise.
A function? We're calling it A. Is it a step function? No, what is it? Accumulation, but what kind of function is it? Piecewise linear. What's our general structure of piecewise linear? Each piece is what structure? What form? Point slope. So, remember, you're going to need, so if we're looking at, say, just arbitrarily looking at the second interval, you're going to need the coordinates of that point and the coordinates of that point, given some x in the middle of the interval, right? So here's our x, just any x value in the interval. So what are the coordinates of that point? And what are the coordinates of this point up here? No, any interval. You're not pulling numbers off. It could be any interval. It could be any interval and any x value in that interval. What's the coordinates of your left point and your right point, and then you're home free with the point slope form. We're using H now. Yeah, you got a mistake there. You mistake there.
Oh, that's what you did.
Yeah, the y coordinate, right? I just want to see if we remember or not.
Get 3B.
Those are the 2 points. So form, right?
Yeah, that's one.
Who remembers? Yes, that's what we're reviewing. So we want to write the form of that segment. So we need those 2 words out. Given one x value 10, so to bring the separate to your so then what's the actual portion
So additional y is going to be
Yeah.
Okay, yeah.
8.
Okay, so I don't want to spend a lot of time on this because it's review. What's the x-coordinate of the left side of the interval? No, left of x.
That's why.
And then what's the y-coordinate? No, the y-coordinate of this point. F of, there's no h involved. We're just here. We're just here at left of x. Left of x.
Oh, okay.
Left of x is the x-coordinate. The y-coordinate is f of left of x. That's the coordinates of this point. Okay? What about the coordinates of our point over here? So now we need the right side of the interval, which is how far to the right of left of x? Plus h. So we're going to start at left of x and we're going to add h to get the x-coordinate on the right side. So it's going to be left of x. I'm not going to have room here, but I'll try. Left of x plus h is the x-coordinate up here at the right side of that interval. And so then what's the y-coordinate? F of that. Right? And we know that to create piecewise linear, the most convenient is our point-slope form. The point-slope form. So it's going to be y equals k times x minus a plus b. A, b, we can use the starting point here, right? This is our a and b. It's the starting point of the interval. And how do we get k? The change in y over the change in x. So we're going to take the change in y, or final y minus initial y, divided by final x minus initial x, which is just what? What's that value? Just h, right? The change in x is just h. So final y minus initial y over, that's k. That whole thing right there is our k. Change in y over change in x times x minus left of x plus b, the y-coordinate of our starting point. Review. Okay, anybody have a question on that? K times x minus a plus b gives us a linear piece, right? A linear piece. As soon as x moves into the next interval, left x is different. And so then we get the next piece, right? As soon as we move into the next interval, then left x is going to be this value, and this whole thing changes. Please. What's that? Yes, this is our approximate accumulation function. It's going to be this piecewise linear function. So this is yes. This is the a of x function. Any other questions? Okay, did you sketch the approximate rate function? Sketch the approximate rate function. If you haven't already. There's a prettier version, okay? So, are these step rates positive or negative? Getting more positive or less positive? Getting more positive or less positive, the rates? Less. Less.
We're increasing that.
No. No. This rate of change is greater than this one.
Yeah, but it's
Well, you keep saying you're saying the rates are increasing. These are getting less positive. These rates are getting less positive. Yes. Yeah, so this constant rate is less than that one, and this constant rate is less than that one. So, and then my intent was that you would pick off these values and do some calculations, but for time's sake, let's just sketch it, okay? So that first constant rate is just under 10. That second constant rate is pretty close to 4. And then the last constant rate is
About 1.
almost 1. So here's where we pick up. Here's where we pick up what we haven't done. So we need a rule for this, what I'm calling R1, the approximate rate function. What rule do we have for this approximate rate function? So in other words, our input of that function is an x value, say right here. And the output then is the constant rate. Just move it back here. Just do it here. So say at 0.6. Okay, the input, x 0.6. The output is the constant rate of change from our approximate accumulation function. So what's the rule for R1? What's the rule for R1? We want to write R1. We want the input x to be this value, and then the output to be the constant rate for the current interval. What's the rule for R1? Work it out with the person next to you. So we want to define this function R1. We want a mathematical formula that gives the approximate rate of change, the step function. If it were any more obvious, it would hit you in the head. If it were any more obvious, it would hit you in the head. Who's got R1? It's right in front of you. Right. We need input x, we need the output to be the constant rate in that interval. We've already done it. We've already done it. Just write it down. Okay, So the answer to that question is we've already done it. Some of you got it. It's K. It's K. That K takes the current x value and gives you the approximate constant rate in the current interval. So we've already done it. We just write it down. Okay, the next question is, how can a better approximation, so is this a good approximation of the exact rate? No, right? So we got these wide intervals, 0.4, big steps, okay? How can we do better?
Smaller H.
Make h smaller. Let's do it. Ready? So this is why graphing calculator is such an amazing tool for us, because with a click of a button, we can just make h smaller and get a better idea. How about the approximate accumulation function now? Is it doing pretty good? Yeah, there's hardly any daylight in there, right? There's a little bit, but it's really close. And so we got a better approximate rate function. Make h even smaller.
Very nearly on the line.
Yeah, and so now our approximate accumulation function is hard to tell the difference with this view of it. And we're getting a really good idea of what the rate function will be. Here's a very small
Virtually
H.
the same.
Very small h.
Virtually the same thing.
What are virtually the same thing? But what's our goal? What's our goal? To get what?
Exactly. Exact.
Exact what?
Exact rate function.
Rate. So we're looking over here at the left, and that is still a step function. It's still a approximate rate, but it's doing a very good job of, well, it's converging on something, right? It's converging on something.
I think your calculator.
Okay, so remember we said, we started with f. We started with f, our exact accumulation function. And so that function is, it's a quartic, all right? So what is it? I'll just write it down real fast here. It's this right here. Can you read that? Okay. That's what this function happens to be. It's a fourth power polynomial, okay? But we know a different way we could write that, right? So we worked for a month to say that accumulation function could be written. So is that closed form or open form? Over there on the left. Closed form. But now we worked hard to say that f of x could also be represented in an open form. And what will that form look like? Okay, so people are saying it. So the integral, right? In this case, from 0 to x of what? Some rate. So I'm going to call that, so some rate function. So because it's an accumulation function, it can be written as an integral of its rate function. And so this is what we're now getting close to, is this rate function. So we're kind of assuming that thing existed because we could write it as because we could write the accumulation as the integral of its rate. And now we're getting close to kind of uncovering what that rate was, what that rate is. So just like before, we're going to talk about making h super, super small, small enough so that we can't distinguish it anymore, okay? And so this is pretty close. But here now I'm graphing the exact rate function. So we've got exact accumulation and resulting exact rate. So the question is, what is that rate function? And more specifically, what is that rate function in closed form? Can we get just a formula like a polynomial or an e function or a sine function that would give us exactly what that rate is? That's our endeavor here. That's what we want. Okay, so let's just review it all together here. black curve is exact accumulation. Piecewise over here is the approximate accumulation, from which we got approximate rate. And then we make h very small, and we get exact rate. Okay, so exact accumulation to approximate accumulation. So exact accumulation is our f function. Where are you? That's f. Approximate accumulation, approximate rate of change, and the red one, exact rate of change. So our goal is a closed form for that exact rate of change. Given we've got closed form for the exact accumulation, we want closed form of the exact rate. Okay, so now, to get this closed form of this exact rate, this form of the approximate rate does not lend itself well to that. If our goal is a closed form for the exact rate, this form of the approximate rate of change does not lend well to developing a closed form for the rate of change. So we're kind of going to start over and approach this slightly differently, okay? So this is what I'm calling approach number 2. Approach number 2, here we go. So here's what we had before. Look familiar, right? Building the approximate accumulation from exact accumulation. What happened? Oh, right. Okay, and this was one interval at a time, right? So we looked at these fixed intervals of width h. And within each interval, we had a constant rate for every x value in that interval. So now, take a look at this. This blue one is where we're going. This is a new way to think about it. Okay? So rather than having fixed intervals of width h, I want an interval of width h that always starts at the current value of x. Do you see that? So we want an interval of width h that always starts at the current value of x, rather than setting these intervals and having x vary through each interval. The interval is going to move with x. It's going to move with x so that the interval always starts at the current value of x, not at these, in this case, not every 0.4. So how is this going to change? So the process that this reverse process, how is this approach going to change it? So so you're looking at it. So I want you to answer these questions as best you can. And I'm going to keep revealing a little bit more at a time, and then you can go back and revise your answers to these questions, okay? So, A through E in approach number 2, number 4, okay? And I'm going to update and add little bit by little bit to the answer. What are the coordinates of that point? That should be easy.
X,
It's the current value of x and f of x. Okay. So now the difference here is for every point like that, we're going to generate a rate of change for the interval h that to the right of it. So we're going to, for every value x, starting at that point, we're going to generate a rate of change for that interval of h starting at x. So first question, are we going to have an approximate accumulation function? Is there going to be an approximate accumulation function? Yes or no? For every, is this exact or approximate? This point right here, exact or approximate? That's a point on the curve. And then when we move it forward a little bit, will the right side be exact or approximate? So now, when I increase x a little bit and look at that left side, exact or approximate? No, it's exact. It's right on the curve. So for every point on the accumulation function, for every point on the exact accumulation function, we're going to have a rate of change. So are we creating an approximate accumulation function? No, we are not. We're taking every point on the exact accumulation function and assigning it a rate of change. There's no approximate accumulation function anymore. Do you see it? Does it make sense? So back here where I drew the point. What rate of change are we going to assign this x value? What rate of change? Or how is it shown? What rate of change are we going to assign this x value? How is it represented? What is representing the rate of change that we're going to assign to this x value?
So the line is a constant, right?
Isn't it the rate of change of this blue line, right? The rate of change of this blue line, just like before when we had the piecewise linear. There's a constant rate of change here. We're going to assign this constant rate of change to this x value. But this is still an exact amount of accumulation, f of x. So we're just going right from exact accumulation to, now, so the next question, is it approximate rate of change or exact?
Approximate.
So this rate of change that I'm going to assign this x value, based on this, is it approximate or exact?
Approximate.
Is it less or greater than the actual rate of change at that x value? Do you see that it's a little bit less? Because we could, if we zoom in on that point, watch. If I zoom in on that point, we can look at the rate of change. No, that's not what I wanted. Over here.
Oh.
When I zoom in, my exact accumulation function starts to look linear. That's the true rate of change. What about our blue line that we're going to calculate? Approximate or exact? That's going to be an approximation. So the slope of that, the rate of change or the slope of that blue line is going to be an approximation to the actual rate, which we can see now by this little piece of the curve. Okay, so where are we on the questions here? We did... Will an approximate accumulation function be formed? No, we're going right from points on the exact to values of rate of change. Will the resulting rate of change of constant rates change abruptly or something else? Remember, we had a step function. Those rates changed abruptly. Will they here, in this case? Will these rates, these slopes of these blue lines, will the slopes of these blue lines, is it going to change slope abruptly? Look at the slope of that blue line. Is it changing in abrupt steps?
No, it's going to be gradual.
No, it's going to be gradual, right? It's going to be continuous. Okay, question C. Will the resulting rate of change function be approximate or exact? We talked about that. If we keep this h at 0.4 like this, we're going to get approximate because the slope of the blue line is a little different than the actual rate of change at the point in question. D, will the approximate rate of change from the two approaches ever be equal? So going back to the first approach. So let me show you, let's go back to this. Will the approximate rate of change ever be equal, and if so, for what x values? Will the approximate rate of change ever be equal, and if so, for what x values?
Yes, for each one of delta x is designated from 0 to 0.4, 0.4 to 0.88, 1.2. So those lines they vary up exactly.
Right, so there are some precise values of x where the interval lines up, right? And which values of x are those? 0, At 0, we're going to get the same approximate rate of change in both approaches. And then, where's the next place? At point 4. Maybe. Takes a steady hand. That's the best I can do. At point 4, the approximate rate from both approaches is going to line up. And at point 8, etc. I had it. It's one more try. Got it.
Bingo.
Okay. But as soon as we get away from the left side of our intervals from approach 1, it's going to be different. Right? So in approach 1, the rate of change, the approximate rate of change is going to be based on this interval of h. It's going to stay the same. But in approach 2, that approximate rate of change is going to continually change. Right now, it's going to be based on this interval of h. Okay, so now, can you write the rule for the rate of change function? So, let's show it. Here we go. So, is it going to be the smooth or abrupt, the approximate rate of change function?
Abrupt.
The approximate rate of change function, smooth or abrupt? Smooth. Okay? Here's the approximate rate of change function. So now, can we write a formula for that? I'm going to call this one R2. R2. Can you do it? So how is it represented? How is R2 the output? So at x, we want the approximate rate of change. How is it represented in this picture? How is it represented in this picture? Not variables, not numbers. How is the approximate rate of change at the current value of x represented in this picture?
Blue line.
What about the blue line?
Slope.
Slope of the blue line. So that's going to be, the slope of the blue line is going to be the structure of your function. Do it. Can you do it? Can you write the slope of the blue line? This is easier than the previous approach. This should be easier. You can do it. Can you write the slope of the blue line in terms of x? Go. Show me. Should have gotten this. What are the coordinates of this point? x and f of x. What are the coordinates of this point? Okay, we're not done. Still have a very exciting conclusion. What are the coordinates of this point? Okay, can I have your attention, please? If you're still talking about the math, go ahead, just whisper, okay? I encourage that, but let's rein in the... So what is the x-coordinate at this point? The x-coordinate. X plus h. X-coordinate. Now we're home free. Change in y over change in x, which is just h. Okay, so here, with this approach, we bypass an approximate accumulation function. We go right from exact accumulation right to, is it approximate or exact rate of change? Approximate or exact rate of change?
Exact. R2.
Remember, this is based on the slope of this line.
Okay, what is your question?
Is this approximate or exact rate of change? Approximate. Okay, let's show. So we already found here's the exact rate of change. We found it before using the other method. Here's the exact rate of change. So how can we make our approximate rate of change better? Smaller h. Let's do it. Ready? Here we go. Smaller h. Now notice over on the right, my interval h is smaller. And so what about that? This is called a secant line. What about the slope of the secant line? How does it do? Starts doing, as you make h smaller, it starts mimicking, right, the rate of change of the actual function a lot better. And so then we see our approximate rate getting closer to the exact rate. Until what? Until h is sufficiently small, right? So now here h is 0.005, and they're virtually the same, right? So okay, so I'm still not done. Okay, any questions? Any questions on the worksheet? So I want to show you really fast. Just want to give you a taste of what's to come. Let's actually get a real accumulation function and use this to get the exact rate of change in closed form. Okay, just do one example of that as a kind of precursor as to what's to come. So tune in. I'm going to go fast. But this first one that you did on the first page was actually, the very first one was the volume of a sphere. Okay? This f function here is f of x equals, okay, if I'm going to make it, I need your attention. X represents what in the sphere? X represents what in the sphere? The radius. The output then is the volume of the sphere. That's what you were doing actually in number 1. Okay? So now we're going to going through that same process, we get, is that over on the left, approximate or exact rate of change? Approximate, okay? Our goal is a closed form for the exact rate of change, which is this red one, okay? Our goal is a closed form for the exact rate of change of volume with respect to radius, which is the red one. Okay, we know visually, we can get that easily visually just by making h smaller. But what about a formula for this red graph? What about a closed form? So let's do it. Here we go, fast. So if, where is it? Come on, it's here. All right. All right, so if we have 4/3 pi x cubed, that says take the input and cube it, multiply by 4/3 pi. Right? That's what this rule says. It says take the input and cube it and multiply by 4/3 pi. So now looking just at this, what's our new input? X plus h. So I'm going to take that input and cube it and multiply by 4/3 pi. What is f of x? Well, it's just that. So we're going to rewrite this using the rule for f. The only hard thing about that is this right here. So our input is x plus h. We're going to cube it, multiply by 4/3 pi, and we're going to get this right here. Do you see it? So that right there is our R2 function applied to the volume of the sphere. Here's our 4/3 pi x plus h cubed, that's this, minus 4/3 pi x cubed, that's this, all over h. Okay, so you're going to like this. Watch. I'm going to rewrite that. Now I'm going to grab this x plus h cubed. Hopefully, there it is. And I'm going to go to math, expand. Boom. All right. No. Okay, then I'm going to, watch this. I'm going to take this 4/3 pi. And I'm going to distribute it. Watch, ready? Here we go. Oh, boom. Come on. Distributed it. What? All right, please. Please, hold on. Okay, now look. Do you see? 4/3 pi x cubed minus 4/3 pi x cubed equals? So that first term and that last term are the same. They're equal but opposite. So they go away. So if I go math, simplify, boom, they're gone. All right, ready? Here we go. Wait, you guys, please. I want to let you go on time. Please don't start talking every time. Watch the video and then go, ooh, nah. Okay? All right. Okay, so now look, there's an h in each one. H squared, h cubed. So if I highlight the h, I can grab it and factor it out. Come on. Come on. There. And so what's h over h? 1, leaving just that numerator in the parentheses. Simplify. So this is the same as, right here, this is the same as the approximate rate of change for our volume with respect to, wait, not done, hold on, you guys. All right, so those are the same. That's the approximate rate of change. And how do we get exact? What do we do to get the exact rate of change? It's very small h. So what happens to this for very small h? Nothing. There's no h in it. What happens to this for very small h? 0, because there's an h in it. What happens to this for very small h? 0, because there's an h in it. Therefore, this thing is the same as 4 pi x squared, and that is closed form for the, what happened? For that red rate of change graph, the exact. That's the exact rate of change in closed form for the volume of the sphere.